Hello, my name is Dave Zilkoski, and I will be moderating this session on real-time network alignment, RTN alignment. Today, we're going to learn about the principles, benefits, and limitations of RTN systems and how to monitor and align your RTN to the National Spatial Reference System. This is a very important topic because there are many DOTs, universities, and private companies that operate their own services. There are 4 parts to this session. There will be 2 presentations with questions following each presentation. So it's my pleasure to introduce the 2 speakers. The first one will be Chase Simpson. He's a professional land surveyor and an associate professor of practice at Oregon State University. Chase received his Bachelor of Science and Master of Science in Civil Engineering with an emphasis on geomatics from Oregon State University. He's an instructor for several surveying courses, including surveying theory, control surveying, and Oregon land survey law. His recent research has focused on developing methods of aligning real-time GNSS networks to the National Spatial Reference System to increase user confidence and consistency between adjacent RTNs. Once again, this is an extremely important topic, and now I'd like to turn the presentation over to Chase.
Thank you for that introduction there, Dave. Let me go ahead and get my screen sharing going real quick. As Dave mentioned, today what we're going to talk about is real-time GNSS networks. We're breaking this up into 2 different parts where a lot of our research associated with how do we manage these real-time networks is going to be covered by William Moheen, who will get introduced here later. And what we're going to focus on is more of the concepts, the principles, best field procedures. We're going to focus on those things as well as kind of recapping some research that has been conducted associated with using real-time GNSS for kind of traditional survey applications. So we're going to be focusing on those benefits, limitations, and best practices here. Before we get started, what I would like to do is talk about and recognize our funding source. So the efforts completed for these efforts, a lot of what we're going to be talking about when William presents his research, a lot of that is funded through 2 different funding mechanisms that we've had. So 2 different research projects. One of them is funded by NOAA NGS, and the other is ODOT. And I want to make sure it's clear that all of these statements, findings, conclusions, and recommendations that we are presenting herein are just those of ourselves, the authors. They're not views of NGS, ODOT, or the U.S. Department of Commerce. So with that said, let's really start diving into what we're going to be covering. So the outline of the talks, as Dave mentioned, we have 4 parts. We have parts 1 and 2. That is going to be focusing on, again, those concepts, principles. So we're going to be covering differences between real-time network observations and traditional RTK or single-based RTK and how they differ. We're going to talk about proper field procedures or recommendations when using real-time networks. And then we'll talk about how do we combine real-time GNSS network observations with conventional surveys. Conventional surveys meaning those of total stations, leveling. So I take those conventional optical measurements and combine them with real-time network observations. This is something that you tend to want to do in practice when you are using real-time network observations to help establish project control. And so we're going to dive into that so we can really leverage this technology and this really GNSS surveying technique for more applications. Parts 3 and 4, that's going to be the Q&A session as well as the discussion of managing real-time networks. So it's less on the user side, more on how are these networks being managed and how can we manage them better to help improve that user confidence? And that will be the section being led by William Moheen. So one of the first questions that I hear all the time is, well, isn't real-time networks, real-time network GNSS, I'm going to shorten that to RTN throughout this presentation, isn't that the same as RTK, real-time kinematic? And oftentimes when people are using these 2 terms, RTK versus RTN, what they're really referring to is a single base real-time network, single base real-time kinematic solution versus a multi-base real-time kinematic solution. And so I distinguish those 2 differently. because one is a network of base stations or reference stations, and the other is just a single station. And so let's look into those a little bit more. So with the single base RTK general concept, what you have is you have a base station that is set up over a known point. We are observing common satellites between our base station and our rover. And what we end up broadcasting are the observables at the base station to our rover. And then our rover goes through and performs these different linear combinations of those observations. Essentially, by taking those different linear combinations of observations, we can start canceling out or minimizing certain errors that are common between the base and the rover. So looking at this, again, we have the base receiver is set up over a known point. The second receiver, the rover, is set up over an unknown point. Data is logged simultaneously at the base and rover. The base data is transmitted via maybe a radio link, Wi-Fi, cellular plan, some method of communication. That data is transmitted over to the rover. The survey is initialized, such that it is using data from both the base and the rover. So data is being processed inside our rover unit. And then the survey is conducted. So when the survey is being conducted, all that processing, again, is happening in the rover continuously. And then the results of processing are what's sent to your data collector and logged for viewing or for potentially post-processing later. All right, so that's our single base RTK. That's our traditional single base RTK method. When we start looking at RTK surveys, these are typically performed using radial surveys, where you have your base station set up, and let's say there's a handful of different control points, or maybe you're doing like a topo survey with your GNSS, and your idea is that you're going to go around and observe all those points. When you are going through and doing this for surveys where you need higher precision, we want to add redundant observations in. So instead of observing these control points a single time, you actually observe them redundantly. So observe them again. Now there's some common rules for best practices on how to do this. Some of those rules are try to keep your baseline distance shorter. The assumption that we're making is that the errors that are occurring at my rover are the same as my base. So when I difference those observation equations, that common error will cancel out. As your baseline distance increases, that assumption starts to fall apart, meaning the errors are not as common between the base and rover. So some rules that I've heard are that you want to keep your rover within 10 kilometers, never more than 20 kilometers from your reference station. For those higher order surveys in single base RTK, typically people are trying to stay within about 2 kilometers of their base station. The idea is, again, maintaining common situations, meaning the atmosphere, the ionosphere, all of that is going to be common between the base and the rover. Now, when we do RTK surveys, the base and rover must see at least 5 of the same satellites. Traditionally, when we're doing GNSS positioning, we only need to see 4. We think of 4 as we need to see 4 satellites or 4 knowns to solve for our 4 unknowns, which are going to be our position in XYZ, as well as our time offsets between our rover clock and the satellite clocks. Now we need to see 5 in this situation for added redundancy and to aid in the initialization of solving that integer ambiguity. So 5 is generally the rule. We'll see that number 5 come up later when we start talking about real-time networks, because some real-time networks will actually have that hard-coded in where they will not give you a fixed solution or an initialized solution until you see 5 common satellites. So some common sources of error in your RTK surveys, and a lot of these are still applicable to RTN surveys, so keep that in mind, are going to be multipath. That's going to be our deflected GPS signals, which can give us erroneous results. Essentially, we get multiple signals from a satellite detected at the receiver. We can have poor PDOP or weak satellite viewing geometry. Your PDOP should always be less than 7. Now that we're all really working with multi-constellation, that is GPS, GLONASS, Galileo, Beidou, right? Now that we're working with more constellations, typically we're seeing that your PDOP is usually less than 3 or 4. If you're in areas where your PDOP is up around 7, chances are is you are in areas that are at much higher risk for multipath as well. So it's blocking big portions of the sky's visibility. Other sources of area are just blunders. So inputting the incorrect antenna heights, or maybe your reference station has that incorrect antenna height. So any error that you have in your base station ends up getting propagated through to your rover in this approach of single base RTK. We'll see this is actually kind of a nice strength to using real-time networks, because if one base station is out, you usually have a bunch of other network stations or reference stations that can help identify that one of those stations is bad. In single base RTK, we don't have that, right? So we have to input good field procedures, good field checks. So the idea of those field checks are, well, when I first start my survey, let me go to a control point that I know, and I'm going to perform this thing that a lot of people call a bench check. So I'm going to take my GNSS rover, and I'm going to observe a point that I know the coordinate of, and I'm just going to do a quick coordinate comparison. Am I getting approximately the same coordinate? That helps ensure that I have a good fix and that I do not have any antenna height errors in either my rover or my base station. We can also have errors such as interference with our radio link, meaning we're just unable to broadcast those observations from the base to the rover. So we're unable to do that differencing to cancel out those common errors. That's similar to not maintaining initialization, right? So we're unable to maintain that initialization. This can be caused for many different things. Cycle slips can really cause this, where we're just not getting a clean signal from our satellites. Satellite orbital errors. When you're doing surveys in real time, we're limited to only using the broadcast ephemerides. The broadcast ephemerides are getting much better, more precise, meaning we have really good predictions of where those satellites should be in orbit in real time. So that is a limitation here. And then the other thing is errors are going to increase as the distance from our reference stations increase. We already mentioned that already. So let's talk about real-time networks, RTNs. These are similar in concept to RTK or single base RTK, but now we have a network of reference stations. There's going to be, those reference stations are going to be controlled by some RTN manager. And one of the benefits to having a network of reference stations is we can better model the tropospheric and ionospheric errors. So we can actually minimize those as opposed to just assuming that they're common between the base and rover and assuming that they're getting canceled out by doing our differencing. In this situation, we can actually apply corrections for the tropospheric and ionospheric delays because we are able to create these tropospheric and ionospheric models through our network of reference stations, meaning they can observe them and create these correction models. Within this, because we're able to create these models to correct for the troposphere and ionosphere, we can actually have slightly longer baselines because our assumption of, hey, the errors at our base and rover are going to be the same. We don't necessarily need them to be the exact same. The tropospheric ionospheric error can be slightly different between our base and rover because ideally we can model and interpolate what the tropospheric and ionospheric delays are at wherever our rover is located because we're creating this full model over that area. So our baseline lengths can get longer. That means that we can work a little bit longer without having to move a reference station, so to speak. We're thinking of it in terms of single base. When we're thinking about these different methods of real-time networks, there's really two most common ones. There's actually a few different methods, but the two most common concepts that exist for real-time networks is this master auxiliary concept, MAC or MAX, or virtual reference stations. These two methods are very, very similar to each other, but they're also quite a bit different. So in the VRS approach, the rover is going to transmit a point or position to the server. So it's going to say, hey, I'm located around this location. The server is then going to assign said position and create an imaginary base, a virtual reference station. Then it goes through and it interpolates what all of the corrections, or basically interpolates a set of observation equations that can then get transmitted from this virtual reference station to our rover. One of the great benefits to a VRS method is you end up with a very, very small baseline vector. We mentioned that our baselines, the smaller those are, the greater we're agreeing with that assumption that the errors at our base are the same as our rover. So when we do the differencing, things cancel out. So yeah, the result is you have 1 to 30 meter baseline lengths with the VRS. The downside to that is your baseline vector is not attached to a real point. It's not attached to a physical point on this Earth. It's a virtual reference station. And so there can be some challenges when you then want to go through and perform adjustments and combine these VRS-derived RTN positions and combine it with leveling or total station observations. It just becomes a little bit more challenging. Now, the master auxiliary concept is similar, but instead of creating a virtual reference station, what it does is we identify a master reference station. So it goes through and it says, hey, you transmitted to the network where you're located in this real-time network. Let's look for the station. Oftentimes it's the station that is the closest to you, but there's some other weights that go into it. For example, how many common satellites are you viewing? So there's a full equation of how they identify which station is going to serve you best as your master reference station. Then what it does is it will actually do baseline differencing between that master reference station, let's assume it chose this one, to all of the auxiliary reference stations, and then it transmits the full observation equation of the master reference station and the differences between the master and the auxiliaries. All of those differences will also get broadcast over to the rover. The rover can then reconstruct those observation equations and then perform all of the differencing similar to what we did with the single base, right? But now we have multiple rovers. In addition to that, it transmits the tropospheric and ionospheric models that the management software has created. So then we're able to have better models for tropospheric and ionospheric delays, and then we get more redundant baseline vectors because we're computing vectors from all of these stations. But what your instrument saves is only a single a single baseline vector to your master reference station. So you only get a single vector in your final solution. But that single vector is tied back to a real physical point. So it makes combining these observations with other data sets a little bit easier. All right, so here's a quick graphic to help us conceptualize the difference between RTK and network RTK. And it comes back to how do we manage those tropospheric and ionospheric delays. So let's look at this and say we have our positioning error in these plots, and we have single-based RTK here, and we have network-based RTK here. And this is kind of our distribution of our reference stations. Again, single-based, we have one reference station. Network, we have a network of reference stations. And so there's our modeled error due to our tropospheric and ionospheric delays. Here, we went through our single base and we were able to identify what that error is and model it. We are assuming that this error is applicable everywhere our rover is. So our rover is just using that same modeled error everywhere. We don't account for the fact that it's actually fluctuating temporally over time and over location. So we end up getting this larger residual. With network RTK, we're using this network of reference stations to get a better model of that error. So now the actual error, it agrees much better. We have a much smaller residual between our actual observed and what was modeled, right? So we end up improving our accuracies that way. So, summary of our RTN benefits. A couple more things. We don't need to set up your own base stations. There's just a network of continuously operating reference stations, similar to this one. This is one of the stations tied into the Oregon Real-Time GNSS Network. So this is all of the Oregon Real-Time GNSS Network cores that are being used. Some of these are NGS cores. Some of them are PBO stations from UNAVCO, and different other sources. So it's a conglomerate of continuously operating reference stations. But we don't ever have to set up our own base. We just get to use this network of them. So we get a little bit more efficiency. The RTN is going to have some management software that helps monitor its own integrity. Essentially, it's performing baseline computations between different clusters of these cores to verify that stations are where they're supposed to be, or that they haven't buried internally. What's important to note here is this RTN management software isn't checking to ensure that these stations are aligned with the NSRS. The typical management software is just verifying that relative to the other stations in this network, they do agree. So we get good relative accuracy from this monitoring, not absolute accuracy. If we go through and we look at this, we get a very dense reference station network, and that's going to help result in shorter baselines. Shorter baselines generally means improved accuracies. The RTN allows us to monitor and model our atmospheric conditions. With single base RTK, we don't usually get to do that. You just do the modeling from one location. And all users of the system are using a common established coordinate system. And most of the time, this is tied into the National Spatial Reference System. So you can get NSRS coordinates in real time. The limitations will obviously cost a lot because there's all of these stations that have to be set up and be managed. A lot of states will require some type of subscription to access these real-time networks, or there's a lot of kind of private companies that will offer these services so you can leverage their RTN that they set up for their applications. You can use it and access it for a fee. You can't use it everywhere all the time. So use is typically limited by cell phone coverage because that's what they're using to broadcast those corrections to you, is a cell signal. And you can also have system downtimes, right? So they could be going through and doing, maybe they're working on their management software. So maybe there's a morning where the whole real-time network might be down, and that's kind of out of your control, right? Most RTN operators are going to be very, very good at letting you know and informing you multiple days in advance of, hey, we have this scheduled maintenance. It's going to be down for this amount of time in this window. So you can plan for it, but it is a limitation. Accuracy is obviously going to be affected by the network density. Some real-time networks are very dense, some are very sparse. The denser it is, the better we can create those atmospheric models, the better we can minimize those residuals. And it can take longer to get a correction signal as opposed to single base RTK. And when I'm talking about the correction signal, I'm saying, what is the time delay for your base to receive those observations from the satellites and for it to transmit it to you? With your single base RTK, it's a simpler setup. It receives the information, it broadcasts it to you, typically by a radio link. And so the time delay can be, 1/2 to 2 seconds. Whereas with the real-time network, you are receiving the network cores are receiving their observations. They're broadcasting it to the management software, typically through some type of network communication. Maybe it's cell coverage or something similar. And then the network management software goes through and does a bunch of analysis, figures out what data it wants to transmit to the rover, and then the rover receives that and reconstructs things. And so the time delay that you're seeing there is anywhere from 2 to 4 seconds. So with those longer delays, that means when you're getting a correction or a position, you want to make your observations a little bit longer because really the correction you're getting is from 2 or 3 seconds ago, right? So we want to keep that in mind when we're using the real-time network observations. All right, so let's dive into recommended field procedures. So Similar to a single base RTK, you can have situations where your reference station, specifically the master reference station, can also have errors, right? And so this is an example of this, but my key takeaway from this example I'm going to talk through is that you still want to be performing your bench checks to make sure you're getting a good correction from the RTN. So in this example, we went through, and this is part of a research project that we did for the Oregon Department of Transportation to evaluate the accuracy of the Oregon Real-Time GNSS Network. And so what we did is they had a control project here with around 25 to 30 control stations, and we observed each of these stations 12 to 13 times. So when I'm talking about these GNSS loops, that's just a repeat observation, right? So we went through and we observed all of these, and sometimes our master reference station was P406, and sometimes it was Newburgh. Both of them pretty close in distance away, 12 kilometers, 16 kilometers. And what we found is if we plotted the residuals compared to our true coordinates, or our most probable coordinates of these stations, we found that when the reference station was Newburgh, we had about a 3 to 4 centimeter bias in our height. And then when we had P406, our groupings were all pretty together, right? So statistically, we found that there was an issue when Newburgh was our master reference station. And what it ended up being was that Newburgh had somehow unthreaded off of its mount about 3 to 4 centimeters. And so they went out and they checked the antenna and they said, oh yeah, look at that. We have a physical error at station Newburgh, and that error was actually getting propagated to our final results. This is what really stemmed some of the research that William's going to talk about, in that, well, we want to be able to detect these types of issues more frequently. We want to be able to detect this so that the RTN manager can know this issue. They can pull Newburgh out of the network so that it doesn't get chosen as the master reference station and affect maybe a whole day's work for somebody else. So that's what we're trying to correct and minimize. So question is, how do I know my RTN position is accurate? Well, we can verify your setup before and after fieldwork. By doing this, what I'm saying is, let's occupy a point that we know the NSR's position on. So maybe it's a benchmark that you've submitted OPA static solutions for, or it's some other survey, you've identified this coordinate and you're confident in it, right? Let's go ahead and at the beginning and end of the day, let's go ahead and check and make sure that we're getting similar coordinates from the real-time network, right? The acceptable range that we typically use, or that's recommended, is a 2 centimeter horizontal and 4 centimeter vertical for an NSR's position, right? But this is something that's very dependent on the specific accuracy requirements for your project. This is something that was generally recommended by NGS as to being like, hey, if you're within this range, that's pretty acceptable for your RTN observations. But maybe you have a project where that's not acceptable. And in those situations, you'll have to identify and specify what that acceptable range is for you. If the results fall outside of that range, there's a couple things you can do. You can reinitialize. You can confirm your antenna height. You can verify your different mount points with the RTN operator. And really what I recommend doing is calling that RTN operator, that manager, and asking if they're aware of any issues. Oftentimes they can look into things on the back end, help identify what that problem could be. So that's usually the order in which I go through things. First, I'll reinitialize. So I'll disconnect from the real-time network. I'll reconnect, solve for those energy ambiguities, get my fixed solution, check again. I'll confirm that my antenna heights are correct. I'll verify I'm using the appropriate mount points. And then if all of those fail, I don't think the issue's on my end, then I reach out to the RTN operator and see if they can help address that issue. Another question you might ask if you're using the real-time network is, how long should I observe? So this is a summary of work that I was not a part of. but it was a study that was conducted here at OSU. This is the reference to that article. You can search it online, or we'll also provide some links in the description of the video. But what this does is it reports the RMSE, or our accuracy, at a 68% confidence level. And they compared results for a single base RTK solution versus a network RTK solution. Now, when they did the single base RTK, they did it using GPS only and GPS plus GLONASS. And then for the network RTK, when they conducted this study, they could only use GPS only. So we were limited to using GPS only. But the key takeaway I want to look at here, so just compare the dashed blue and solid blue to the dashed blue and solid blue up here. What we're seeing is our overall accuracy. Again, what we're looking at is accuracy on the Y and the observation duration on our x-axis for both of these plots. And what we're seeing is generally you don't see a great improvement with your longer observations. That's not to say you should just do 5-second observations all the time, because these stations that were observed for this test, we picked ideal stations, meaning they had optimal sky visibility, 0 multipath issues, everything was great. The more sky visibility issues you have, the more multipath you are susceptible to, the longer your observations you're going to want them to be, right? Or the more confidence you want, observe for longer. But what we're seeing is we didn't really see a big trend or a big difference between observation durations in either of these approaches, single base or network based. But if we compare single base to network based, we saw a pretty significant improvement. So if we're looking in the vertical, we saw the RMSE for network RTK, even if we're, say, looking at this 180 second observation duration, 3 minutes, we found it was around 2.2, 2.3 centimeters. Whereas if we look at single base RTK, we're looking close to 3.8. So we saw a significant improvement in the vertical there. And then in the horizontal, we also saw some improvement. So up here, we're looking close to 2 centimeters in the horizontal. And now we're looking at 1.5. So where we saw the most improvement was actually in the vertical of our network solutions. Okay. So now the question is, all right, well, surveyors love redundancy, right? If we get redundant measurements, we can do least squares adjustments. We can start figuring out our errors. And so how many observations should I make? Should I make 1? Should I make 2, 3, 4, 5? This was a study that I was a part of, that I was leading. And what we did is we took the results of this study and we said, all right, let's assume that we're going to, for control applications, I want to make a 5-minute observation, right? So what we did is we said, let's observe all of those stations, those 25 to 30 stations that I mentioned before. Let's observe those 25 to 30 stations for 5 minutes each, but then let's observe them redundantly, once, twice, 3 times, 4 times. And then let's combine those redundant observations via least squares adjustment and see what our results look like. And so this is what that plot looks like over time. Note our sample size of 5 repeat observations and 6 repeat observations was pretty small. So that's why we're seeing some weird artifacts happening over here. But if we look at this kind of trend going from 1 to 4, what we're seeing is our confidence improves, right? Our error bars continue to get smaller and smaller, and our overall accuracy at the 95% confidence level also improves. And so if we look at this, the improvement is starting to flatten out after 4 repeat observations of 5 minutes each. We found that our vertical accuracy was about 1.6 centimeters and our horizontal accuracy was about 1. Again, I'm combining these via least squares adjustment. I'm not just averaging the final coordinates, okay? If we compare this to OPUS rapid static, which would be a similar observation duration at 20 minutes, all right, because we did 5 minutes times 4. Here we're doing 1 20-minute observation. The accuracies that we're typically estimating out of there is around 6 centimeters or 6 centimeters in the vertical and about 2 centimeters in the horizontal. So of these studies, there's been some other ones that are very similar. There was a lot of effort to go through and replace some standards and recommendations from NGS. So NOS 92, that document is a replacement for NOS 58 and 59, which are two standards and recommendations for leveraging GNSS observations for height monitorization or for establishing control, specifically using OPUS. And so in this replacement, those results that we just talked about actually made their way in. And so to achieve certain vertical accuracies, they started saying, well, hey, actually, we can get some of these higher level accuracies using network RTK, or in other words, real-time network observations instead of static GPS. So this is one of the biggest improvements. This was from an initial draft of NOS 92. I recommend you go and you actually look at NOS 92 for these results or what their final recommendations were. But the general trend is what we're seeing is, hey, we could incorporate redundant 5-minute observations of GPS only or GNSS and be able to attain some pretty tight vertical accuracies with GNSS. All right. So how can we continue to improve our RTN observations? The general recommendation is, I mentioned that we combined our observations in a least squares adjustment. And so the way that we can improve our RTN observations is collect redundant data and then combine that data in a least squares adjustment. So I want to talk about the process that we implemented to do this, and we call it a hybrid network. It's hybrid because it's combining static observations with real-time observations, right? So what we do, let's again say you collect your RTN data. So you did 5-minute observations for each independent redundant observation, right? And so that's what we're looking at here. So we have our master reference stations and we have our control points that we're trying to observe, our passive marks. We get our baseline vectors from those different observations back to our master reference stations. And then we go through and we say, okay, well, let me try to position these master reference stations relative to the NSRS. And to do that, we're going to align them to NGS cores. So now we have these NGS cores. These, again, are our master reference stations, these yellow dots over here, and now they're black dots. And so what we're going to do is we're going to position those using our traditional static post-processing approaches. And then we are going to update the positions of those master reference stations. And then we'll do a least squares adjustment that combines these RTN vectors with these static vectors here. And so this is what we did. This is how we combined things. We have static baseline from cores to master stations, and then we have real-time network baselines from master station to survey marks. If you want to read more about how to do these hybrid networks, I would recommend you look at these two studies, Weaver et al. From 2018, as well as this Gillens et al. 2019 study. They both describe the approaches and the overall accuracies that they were able to attain through this hybrid network implementation. All right, so let's switch gears again, and let's talk about project control. So I want to go through and I want to implement some project control for a transportation project. Typically for project control, GNSS isn't enough because GNSS is going to be good at giving us some absolute accuracy, but oftentimes the relative accuracy is not good enough alone with GNSS. And for that, we usually will want to use one of these conventional instruments. Maybe we use our total station, maybe we're using differential levels to tighten our vertical. And so what happens if we start tying in RTN GNSS with these different methods? One note for the rest of this presentation, when I'm talking about angles or total station data, I'm going to be referring to those as sets of angles, so redundant sets of angles measured with the total station. I think that's a Leica term. That's what I used in this presentation. And then I also reference back to differential leveling. So what happens if we add sets of angles to the network? So again, that same study I talked about before where we made repeat observations. What happens if I take those repeat observations combine them in the least squares adjustment using that hybrid survey workflow, but then I add in sets of angles into each of those. So what we found in the horizontal, we had pretty big improvements. So this is our accuracy with GNSS only is our dashed line. And then GNSS only in the horizontal, again, dashed line. So we have our vertical is kind of this orange, and then our GNSS horizontal is this darker color. So what we saw was pretty big improvements there. Specifically, we saw big improvements in our horizontal, which makes sense because when we're turning our sets of angles, what we're generally finding is that's going to improve the horizontal the most. It was about a 40% improvement compared to our current spec with only 2 repeat observations. By current spec, what I'm talking about is Oregon Department of Transportation's current recommendations for establishing project control, which requires sets of angles and then static GNSS observations on a subset of those stations, right? So we're able to get comparable results here. Obviously, the more RTN redundant observations we make, the better we end up getting. In the vertical, we found that our vertical elevations kind of just stabilized, but we didn't really see a significant improvement. It just kind of stabilized what the accuracy was, which makes sense because GNSS is the weakest in the vertical. So it would have been an interesting result to see it improve things here, right? So what happens if we add leveling to the network? We can probably expect this. I have the plots over here, but in the horizontal, we don't really expect any changes. But in the vertical, obviously adding leveling, because it is a more precise data type, it's going to control our adjustment, assuming we are weighting things correctly in our least squares adjustment, right? And that's a really important concept. We need to make sure that we are weighting things appropriately. So that means our stochastic models we create in the adjustments need to be appropriate, okay? We'll talk a little bit more about that in a minute. So significant improvements when we incorporate leveling data. Okay. Now, question we might say is in those studies that I just showed, those plots, we observed all of the stations with real-time GNSS observations. That can be pretty time consuming, right? So what if we only observe a subset? So if we're following current procedures that people tend to implement, they will only observe a subset of stations with GNSS, right? Maybe 4 to 6 of these control points will be their primary control, in which they'll observe GNSS with them as well. So if we select 4 stations, typically the 4 we're going to select are ones that encompass our entire project, right? So I want to create basically this envelope that surrounds our project. So I'm going to select my points such that they do that. So if I select these 4 points, and now I combine the data again with leveling and our total station data, but I only observe these 4 points, how does that affect our answers, right? So if we look at this, we're kind of showing it all on one right now. So I have GNSS only, GNSS plus leveling. So the GNSS only is obviously I observed all of the stations. GNSS plus leveling, it's all stations plus our leveling. For GNSS only plus total station. And then we have that in both the horizontal and the vertical. I'll show you on the next slide. So these are all the different combinations of what we're seeing here. And if we go and we look at this, again, we see there's generally not a lot of improvement that occurs beyond 4 redundant observations with any of these different combinations of data in the horizontal. And we see that if we want to improve our results the best, right, we are going to actually observe all of the stations with GNSS and combine it with total station data. If we only observed 4 stations or a subset of those stations with GNSS and combine it with our total station and leveling, again, we get pretty good results, but we do see a difference between them. So there is value when we are observing all stations versus only 4 stations. We had about a 50% improvement there. So there is value in adding that effort in there, right? But project specific, maybe you don't need it. We're looking at the vertical. If you don't need the accuracy to be less than around 1 centimeter in the vertical, you don't need leveling. If you need it to be less than about 1.5 centimeters, you're gonna have to do some leveling. So in general, we had about a 95% improvement when differential leveling is performed versus when it's not. No matter if you are doing just 4 GNSS stations or you're observing all of them, it didn't really change. And this makes sense because differential leveling is a very simplistic surveying approach. There's very few systematic errors or instrument errors that can affect our observations, and it results in very precise vertical data, right? So it makes sense we're going to see that constrain and control our least squares adjustments when it's incorporated with the GNSS and total station data. If sets of angle survey is being performed, we did find that repeat observation does have very little effect, but it is still recommended. So what I'm saying is if I go through and I use total station data, my sets of angles, right? So we're looking at these ones over here. We found it didn't really matter if I observed 1 station versus 4 stations. There was very little improvement, right? Because that total station data is helping constrain our vertical a little bit better. All right. Again, doing RTN GNSS only, there's not really much benefit beyond doing your 4 observations per station. We, out of this project, came to this final conclusion of, all right, if you want to achieve this accuracy, what sort of work should you perform? And so we created this table. If you want, you can check out the study and these final recommendations, but it's essentially if you're using the RTN, because that's where we tested this. If you're using different real-time networks, I recommend you kind of run your own study and figure out what is achievable for that network. But if you're in Oregon using the real-time network, these are generally what our recommendations are based off of all of that analysis that we had done, right? So if I want to achieve a vertical accuracy of 1 centimeter in the horizontal, I should do 4 independent 5-minute NRTK observations. But if I'm just using GNSS only, I'm not going to achieve that in the vertical, right? I'm going to start combining it with other observation types. Now we start getting to the point, again, if I want that 1 centimeter vertical accuracy, I could do 2 independent 5-minute RTN observations on each station, or some static GNSS surveying following the NGS specs and adding in that total station traverse data. Or if I want to achieve it in the vertical, I'm going to need to incorporate our differential leveling. All right, so just remember, results can vary. Your results are going to vary based on sky visibility, multipath, PDOP, reference station health, network locations, baseline lengths. As with any survey method, it's up to the job of the surveyor themselves to manage their error budget, right? So you can't just assume you're using the RTN, someone else is managing that. They should be giving you the accuracies that you desire. It's a function of a lot of things, right? So we still have to balance those. This is an example of 2 spherical photos looking straight up from some stations. In both of these, you're going to see some issues. This one, we have less sky visibility. We're working right next to this building, so less sky visibility, potentially some multipath. This one here, we are working next to this big metal pole. Again, we're going to have some multipath issues. So results will vary, right? It's also going to vary based off of the density of the RTN network that you're using. How dense are those cores? In the Oregon real-time GNSS network, we have very varying densities. If you're working out east, well, the stations are spread out a little bit more. You have less topographic variations. You have less storm fronts moving through. So it ends up working out okay, as opposed to over here, we have really high density. So your baseline lengths are always going to be much shorter, right? So results are going to vary. In this study, we conducted our analysis predominantly in the Willamette Valley, around the Portland metro area, just because that's where the majority of users of the RTN are. And so we could expect maybe as we moved out east, the results would actually be a little bit worse. How could we compensate for that based off of these recommendations? Well, add in more redundant observations, right? Maybe go through and do your own mini assessment to evaluate if you're getting those accuracies that you expect. And some additional considerations. You need to select control station locations to allow for GNSS observations. Again, we want to limit multipath, maximize sky visibility. Try to plan your survey such that you can minimize PDOP. There's many different survey planning tools out there that exist. Trimble Business Center has some capabilities like Infinity does. There's some web tools, gnssplanning.com, Trimble GNSS Planning. There's all these different tools that exist that can help you plan your surveys to minimize PDOP. And again, it's your responsibility to make sure that you're getting good results, not the RTN that you're using. So always perform those bench checks, right? It's going to help you catch blunders and be more confident that you're getting good corrections and solutions from your RTN. And with that, that will wrap up this portion of the video. I always welcome questions. So if after watching this, you have questions, you want to reach out, feel free to send me an email. It's just chase.simpson@oregonstate.edu. Happy to work with you. Happy to help you plan maybe a survey where you can assess the accuracies of your RTN network, or just generally talk shop. So with that, we will transition to part 2, which will be a Q&A session.